Hello. We're now on part 2 of the course, where the focus is going to be on things like statistical power and simulating data where there are real effects, or trying to simulate data maybe from your an experiment that you're planning to run. Going back to the beginning, what I said at the start of the first session in this course was that there were all these different reasons for simulating data. But what is really interesting is to simulate data where you've got an anticipated effect in there, and then you can really check out, will your analysis actually show up that effect in the way that you hope? One of the things this really is important for is helping to decide what sample size to use, and that's what we're focusing on today. So simulating data is something that is seldom done when people are planning experiments, at least perhaps more so now, but for many years it was actually not very feasible to do because we didn't have the sort of free software and the computational power to do it. So what people would tend to do is to have a bright idea, then collect some data, and only at that point think about how to analyze it. And then they would often hit problems and try and take an advice from a statistician. And statisticians are not necessarily going to be very helpful at that point because, like Ronald Fisher, they'll tell you that you should have come to them a lot earlier. And as he says here, to consult the statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. He can perhaps say what the experiment died of. So that's all a bit depressing. So you really want to avoid that. But what you can do is do your experiments following this sort of track where you have a bright idea and then you simulate data for the experiment you plan to do, and you think about what the variables are going to look like, and you think about then how to analyze your simulated data. And if at that point it looks as if you've got problems, you can take advice from a statistician before you've actually collected your data and be fairly confident that the analysis you're going to do is likely to show what you want, in the sense of either testing a hypothesis and either getting evidence for or against. Now, one of the reasons that people tend to design experiments in ways that are not optimal is because of basically the way our brains work make us fail to appreciate the importance of sample size. And this has been known about for many years. It was some beautiful early work by Tversky and Kahneman. Kahneman subsequently got the Nobel Prize for economics because the insights of some of his psychology experiments for how we think about economics, amongst other things. But the basic bottom line of their work, they did a series of simple studies showing that people often have a very strong intuitions about random sampling, but they're often wrong. And even when they studied trained scientists, they found these false intuitions were really very dominant when people were asked to judge particular situations. And then in scientific inquiry, you would find people would be doing studies where these false intuitions would be percolating through. This is one of the sorts of problems that they use in this in their studies. So they consider the situation where you've got a town served by 2 hospitals. And in the larger hospital, there's about 45 babies born every day. And in the smaller hospital, about 15 babies are born each day. 50% of the babies are boys, but obviously the exact percentage is going to vary day to day, sometimes higher, sometimes lower. So the question is, if you had a period of 1 year of observations and each hospital recorded the days on which more than 60% of the babies born were boys, which hospital would record more of those days? Would it be the larger hospital, the smaller hospital, or would it not make any difference? Would it be about the same? Just think that through to yourself. I mean, I've warned you that your intuitions may be wrong, but just probably don't overthink it at this point, but just see, do you have an intuitive sense of what the answer would be? We're going to simulate this sort of thing later on, so you will be able to check it out. And the answer is a smaller hospital. A lot of people think it will be about the same. It shouldn't really make a lot of difference. And some people actually think it's the larger hospital because somehow they have more babies. What you can do is work out the expected value in this simulation, because it's really essentially a binomial thing that you're simulating, because it can be a boy or a girl, and you know the true proportion is 0.5, and so you can just draw a lot of simulated data from the binomial. That's what's depicted here in this plot, where we've got blue depicting the proportion of boys if you're drawing from 45, a sample of 45, and that sort of ranges from about mostly sort of 30% to 70%. And then the red is showing you the situation when you've only got 15 babies born on average each day. And what you see is that the red lines are much spikier. They go up and down much more and cover a much greater range. And that's essentially that the smaller sample is giving you noisier estimates. And so the red line is bouncing around, and we were asked to say how many will be above 60%, which is shown as a dotted line here on this plot. And you can see that in the red sample, there's a lot more above that dotted line. It's simply that there's more variability in a sample taken from a smaller, when you take a smaller sample, the estimate. In both cases, the mean is 50%. So the mean is not really affected by the sample size, but it's more you're taking repeated samples of that mean. It's the variation in the observed mean that is greater in a smaller sample. And basically, the human brain isn't too bad at reasoning about means, but it is not very good at reasoning about variance, and that illustrates it in that example. So we're going to run a little script called sampling demo, and that shows you how estimates of the mean of a sample vary with sample size, for sample sizes of 10, 20, and 40. I'd like you to try modifying the script to extend the sample size right up, just to keep doubling it until you get to 640. And I'll just come out of here, and I've got this script loaded up so that I can just briefly show you what it looks like. Here we are. So it's quite a short little script, and if you run it, you should see a plot of estimates of the mean against sample size. In this case, we're not looking at the binomial distribution, we're looking just at the normal distribution yet again, and we're looking at means taken from a normal distribution. I think that's what I did. Anyway, we'll see. So then what I've asked you to do is to just sort of play around with different sample sizes. In addition, you might want to try different sorts of random numbers from different distributions, not just the normal distribution. And there's there's lots of information about this on the web if you just type R random distributions, random numbers, but you can modify this line, and you could put in a different sampling distribution and again see what the data look like. And that's it for this one. So I'll leave you to try that out, and then we'll come on to part 2.